In this video, we get to discuss how we find the internal resistance of a cell using a potentiometer. This is Kisembo Academy. Now, this is how our setup will be like. Of course, our potentiometer, it's having a driver cell right there. With a certain switch we've called K1, this is connected to a slide wire AB. This is the primary circuit. So to it is connected the secondary circuit, which is comprising of the cell whose internal resistance we want. We call this is the cell, and now that, of course, this internal resistance small r is embedded inside the cell, but we'll represent it like that. So it is as though it is in series with the cell, but actually this internal resistance is inside that cell. So this is the cell whose internal resistance we want. Then we have a resistor whose resistance is variable. Then we have K2, K3, and then we have this protective resistor which is meant to protect the galvanometer from excessive current. So there will be two major procedures here. The first major procedure is, first we are going to balance this cell whose internal resistance we know. We are going to first balance it against this slide wire, and we do that when this K2 is open. And then afterwards we shall close this K2 so that we bring it into the circuit, and then we adjust this rheostat to a suitable resistance, and we will be able to balance this whole apparatus or this whole combination against the slide wire, and we'll be able to get what we want. So let's get started with the experiment. So first of all, we are going to first balance this cell against the slide wire. We do that by first of all closing switch K. When we close switch K, of course it means that now this driver cell is going to start providing current. When we close switch K, that is while leaving K3 and K2 open, we move this slide jockey along the wire AB, and we tap it along the wire up to a point whereby the galvanometer shows no deflection. Now when we get that point where the galvanometer shows no deflection, that is the point that the balance length that will correspond to that point, or the point we will have gotten, will be just an approximate balance point. Why? Because when we connected this in the circuit, we have a protective resistor that is in series with the galvanometer. So when we get the approximate balance point, now we go ahead and get the actual balance point by closing off K3. Now when we close K3, in essence we are bypassing this protective resistor. So in essence, as current is, we'll bypass it when we close K3. When we close K3, we continue to tap this jockey along the slide wire AB until we're able to get the approximate or the accurate balance point. And when we get the accurate balance point, that is when K1 is closed and when K3 is also closed, while K2 is still open, we're able to get our first expression. And that expression is E is equal to KL naught. The EMF is equal to K, which is the PD per centimeter or the PD per unit length. Multiply that by the balance length we got. This balance length L naught is corresponding to the potential difference when we balance this cell whose internal resistance we want across the slide wire. So our next step now is to adjust. We now go ahead and adjust this variable resistor so that it attains a suitable value. And then after adjusting this rheostat until it gets a suitable value, we balance it against this slide wire. How do we do this? So with K1 and K2 closed, while K3 is still open, an approximate balance length is going to be obtained by sliding this jockey or by tapping it along the wire AB until we get a point whereby the galvanometer shows no deflection. So after getting that approximate balance length, that is when the galvanometer is not showing any deflection, when K1 and K2 are closed, we go ahead and close K3. After closing K3, it means we've bypassed the protective resistor. So we go ahead and tap this jockey along the slide wire AB until we get the actual balance length. So when we get the actual balance length, we are able to get, we know that when we get the balance length, the potential difference across this resistor is going to be equal to the potential difference across the balance length we've got obtained. And so it means that PD across this resistor IR is going to be equal to the potential difference across the balance length, which so happens to be the PD per centimeter or the PD per unit length. Multiply that by the balance length, and in this case our balance length will be L. So this is what I was saying, that the potential difference across this resistor, now that we've connected it into the circuit, R, which is the current going through this, times R, which is the resistor here of this variable resistor, is going to be equal to the potential difference across the balance length, which so happens to be the PD per centimeter or the PD per unit length. Multiply that by the balance length that we got. So we have our second expression here. So now that we have now two equations, now we go ahead and find the internal resistance of the cell. So just like I've been describing, so we go ahead and repeat the experiment, using different values of R. It means we're going to keep adjusting this rheostat so that we get different values of R, and as a result we get corresponding values of L, the balance length. We go ahead and tabulate those results, but as we tabulate those results, we include in our tables of results the values of 1 over capital R, 1 over L, the balance length that is corresponding to R. So when we tabulate our results that are having values of 1 over capital R and then values of 1 over L, L being the corresponding balance length that we are getting, that is when we are able to find the internal resistance of the cell. Of course, when we draw our graph, the y-intercept, which so happens to be negative 1 over R, is where we are able to extract our internal resistance of the cell. So this intercept is the same as 1 over negative R. Of course, when we make R the subject of the formula, we are able to get our R being equal to negative 1 over the intercept. So now what is the theory behind this? How do we arrive to this? This is the theory behind the experiment. Remember from earlier, we first balanced the dry cell whose internal resistance we want against the slide wire, and when we did so, this is the expression we got. Then thereafter, we connected this variable resistor into the circuit by closing switch K, and when we connected this variable resistor into the circuit, into the secondary circuit, we balanced this combination against the slide wire, and we were able to get another expression. And that was the expression we got at balance. So these two expressions, the first one and the second one, are the ones that are going to be our basis to explain the theory that helps us to get the internal resistance of the cell. So these are our two equations. This is the first one, and that's the second one, like I had showed you earlier. So looking at this second equation, of course, IR is equal to K times L. Now remember, this is coming from the secondary circuit. In the secondary circuit is where we are having a cell whose internal resistance we want. And since we are having the internal resistance that we want, this value of I, which so happens to be the current, can be expressed in terms of this, from this formula. We've explored this formula in our previous examples. EMF of a cell is going to be equal to I times the effective resistance of the external circuit plus the internal resistance of the cell. Remember, the internal resistance of the cell is always in series with the external circuit. So when we make I the subject of the formula, in this case, this is the expression we get. When we get this expression for the value of I, we go ahead and substitute this expression in that portion I here. So this I is this, it's what we've done here. We've gotten this equation 2, and we've substituted for the value of I, as we've put E over R plus R in that value of I, times R, which is that R is going to be equal to K times L. And here we have our equation 3. So now we are going to deal with equation 3 and equation 1. And these two equations, we are going to divide them. When we divide those two equations, equation 1 by equation 3, E divided by that is going to be equal to, this is the portion of equation 1, and that is the equation 3. When we divide this, of course, E divided by this expression, this becomes multiplication sign when this becomes the reciprocal. So that's how it becomes E times the reciprocal of this, which is R plus R, divide that by ER, is going to be equal to this over that. Of course, from here, E and that, these two will cancel. Even this K and that K will cancel. You remain here with L naught over L. And here you have R plus R over capital R. So right there, this banding, this is the same as R over R plus small r over capital R is equal to L naught over L. That's the expression we have. Of course, this R and that R will cancel. You remain with 1 right there. So it becomes 1 plus R over capital R is equal to L naught over L, which is just this step. So we divide through by R so that we have 1 through. we divide through by small r. When we divide through by small r, this becomes 1 over r, like here, is equal to, of course, r over capital R here. The r's will cancel, is going to be L naught over LR. That explains our next step. So this becomes 1 over small r plus 1 over capital R is equal to 1 over L times L naught over R. We simply separated this expression into 1 over L, and we put this expression on its own, L naught over R, like that. And definitely we will end up, when we push this to this side of the equation, it becomes minus 1 over R right there. So it becomes 1 over R is equal to that, minus 1 over R. And when you look at this closely, it's in the form of y is equal to mx plus c, where our value of y is 1 over R, our value of x is, and our value of c is right there. So that is why we say that for us to get the y-intercept, we plot a graph of y, which is 1 over R, against x, which is 1 over L. And this is the graph we plotted. Our value of c is the y-intercept, which is negative 1 over R, which is right there. And it is from here that we are able to get our internal resistance. Our value of x is 1 over L, which so happens to be the x-axis. And our value of y is 1 over capital R, which is right there. So it means that when you are tabulating your results, you make sure that in your table of results you include values of 1 over capital R over 1 over L. And that is how we get the internal resistance of a cell using a potentiometer. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia, helping you manifest excellence.